Blood moon. You hear it everywhere. Headlines scream it. Social media explodes. But barely anyone asks what actually turns the moon crimson, or why some eclipses make it vanish entirely while others leave it glowing like molten copper. Forget the poetic language. Forget the prophecies. We are going to break down the mechanisms, the geometry, the documented varieties of lunar eclipse that scientists track and civilians misunderstand. Earth, moon, shadow. 3 elements, 7 distinct configurations, some visible for hours, some invisible unless you know exactly when to look, which ones kill the light completely and which ones barely dim the glow. This script is researched and factual using sources from NASA Goddard, Spaceflight Center Eclipse Predictions, published through October 2025, Fred Espenak's canonical eclipse tables spanning 6 millennia that cross-reference with eclipse-wise databases, and peer-reviewed atmospheric optics studies from the Journal of Geophysical Research, dating back to Danjon's original 1921 photometric measurements. Now back to the information. Twice a year, the geometry lines up. The moon crosses the plane where Earth's shadow sits. Those windows are called eclipse seasons. Each season lasts roughly 35 days. During that window, if a full moon occurs, you get a lunar eclipse. If a new moon occurs, you get a solar eclipse. The next eclipse season repeats in roughly 6 months. This cycle has been tracked since Babylonian astronomers logged eclipse intervals on cuneiform tablets around 700 BCE. That ring is every sunrise and sunset on Earth happening simultaneously, refracted through the atmosphere and bent into the shadow. The outer shadow is the penumbra, partial shade. Earth only blocks part of the sun. From the moon's surface, you would see Earth taking a bite out of the solar disk, but not covering it entirely. The brightness drops, but not dramatically. The umbra at the moon's distance stretches roughly 9,000 kilometers across. The penumbra reaches over 16,000 kilometers. Those dimensions shift slightly depending on where Earth sits in its own elliptical orbit around the sun. When Earth is closer to the sun at perihelion in early January, the shadows are smaller. When Earth reaches aphelion in early July, the shadows expand. Aphelion adds several minutes to the maximum possible duration of totality. On March 25, 2024, a deep penumbral eclipse crossed the Americas. Penumbral magnitude hit 0.9577. That means over 95% of the lunar disk entered the penumbral shadow. The moon dimmed noticeably. A faint, dusky shading spread across the northern half. Peak eclipse occurred at 0712 UTC. Duration ran 4 hours and 39 minutes from first contact to fourth contact. The entire event was visible from most of North America, all of South America, Western Europe, Western Africa, Japan, and the eastern half of Australia. Fred Espenak calculated that observers could detect the dimming with the naked eye starting around 0625 UTC, when roughly 2/3 of the moon sat inside the penumbra. Before that moment, the brightness drop was too subtle for human vision to register. The moon sat in the constellation Virgo near the descending node of its orbit. This eclipse belonged to Saros, Series 113, number 64 of 71 eclipses in that series, stretching from April 29, 888 CE through June 10, 2150. Penumbral eclipses are the most common type. Over a 5,000-year span from 2000 BCE to 3000 CE, 36.3% of all lunar eclipses are penumbral. Only 3% of those are total penumbral eclipses, where the moon stays entirely within the penumbra without touching the umbra at all. Curved. You can see the geometry of Earth's spherical shadow projected onto the moon. Ancient Greeks used this observation as direct proof that Earth is round. On September 18, 2024, a partial lunar eclipse occurred with an umbral magnitude of 0.0869. Only 8% of the moon's diameter dipped into the umbra. The northern limb crossed just 3.1 arc minutes into the shadow. Peak eclipse hit 0244 UTC. The partial phase lasted 63 minutes. Visibility favored the Americas, Eastern Asia, Australia, Western Europe, and Africa. Because the eclipse was so shallow, it resembled a penumbral eclipse more than a classic partial. The moon never turned dramatically red because most of the disk remained in either the penumbra or direct sunlight. The event occurred at the ascending node in Pisces, 0.4 days before perigee, when the moon reached its closest approach to Earth at roughly 357,000 kilometers. Perigee happened on September 18 at 1328 UTC. This proximity made the moon appear 31.8 arc minutes in diameter, slightly larger than average. The eclipse sat in Saros Series 146. A total lunar eclipse occurs when the entire moon passes into Earth's umbra. This is the blood moon everyone talks about. Totality. The moon does not go black. It glows red, orange, rust, or sometimes dark brown, depending on how much volcanic ash, water vapor, and aerosols sit in Earth's atmosphere at the time. Sunlight hits Earth's atmosphere, blue wavelengths scatter away. Red and orange wavelengths refract through the atmosphere and bend into the umbra. The moon receives only this filtered light. The effect resembles every sunrise and sunset on the planet, shining onto the lunar surface at once. On March 14, 2025, a total lunar eclipse occurred at 0647 UTC. Umbral magnitude reached 1.1804. The moon passed well into the center of the umbra. Totality lasted 65 minutes and 48 seconds. The entire event from penumbral start to penumbral end ran 5 hours and 17 minutes. Visibility covered Europe, most of Asia, most of Australia, Africa, North and South America, the Pacific, Atlantic, Arctic, and Antarctica. The moon sat 3.3 days before apogee, making its apparent diameter smaller at roughly 29.5 arc minutes. When the moon reaches apogee at its farthest point from Earth, around 406,000 kilometers, it moves slower through Earth's shadow because orbital velocity decreases with distance. This extends the duration of totality. Conversely, when the moon is near perigee, it races through the shadow faster, shortening totality. The March 2025 eclipse was the first in an almost tetrad sequence. The second total eclipse followed on September 7 to 8, 2025. The third arrived March 3, 2026. The sequence broke with a partial eclipse on August 28, 2026, preventing a true tetrad. A tetrad requires 4 consecutive total lunar eclipses with no partials in between, each separated by 6 lunar months. The September 7 to 8, 2025 total lunar eclipse lasted longer than any since November 8, 2022. Totality stretched over 1 hour and 22 minutes. The entire event, from penumbral entry to penumbral exit, ran 5 hours and 55 minutes. Peak eclipse occurred at 0212 UTC. Umbral magnitude hit 1.3627. Visibility favored Europe, Asia, Australia, Africa, and parts of the Americas. Roughly 85% of the world's population had a chance to observe at least some phase of this eclipse, because the path crossed heavily populated regions, including Russia, China, and India. The moon entered the constellation Leo at the start of the eclipse and crossed into Virgo shortly afterward. Planetary context added visual interest. Saturn appeared near the moon during totality, sitting like a bright star either to the left or right, depending on the observer's hemisphere. On the evening of September 8, Saturn moved even closer. From Earth's perspective, observers saw Saturn and the blood moon within a few degrees, illustrating the flat orbital plane of the solar system. This eclipse occurred roughly 3 days after apogee on September 4 at 1851 UTC, extending the duration of totality because the moon's slower orbital speed kept it inside the umbra longer. The shortest total eclipses last only a few minutes when the moon barely skims the edge of the umbra near perigee. On April 4, 2015, a total lunar eclipse lasted only 4 minutes and 43 seconds, the shortest of the entire 21st century. The moon grazed the northern edge of the umbra, dipping just barely into totality before exiting. Conversely, the total lunar eclipse of July 27, 2018 lasted 103 minutes, because the moon passed almost centrally through the umbra near apogee. L equals 0 means very dark eclipse, moon almost invisible especially at mid-totality. L equals 1 means dark eclipse, gray or brownish coloration, details distinguishable only with difficulty. L equals 2 means deep red or rust-colored eclipse with very dark central shadow while the outer edge of the umbra remains relatively bright. L equals 3 means brick red eclipse with the umbral shadow usually showing a bright or yellow rim. L equals 4 means very bright copper red or orange eclipse with the umbral shadow appearing bluish and showing a very bright rim. Volcanic eruptions dramatically affect Danjon ratings. When Mount Pinatubo erupted in the Philippines on June 15, 1991, it ejected roughly 10 cubic kilometers of volcanic ash and 20 million tons of sulfur dioxide into the stratosphere. Subsequent lunar eclipses for the next several years appeared exceptionally dark. The total lunar eclipse of December 9, 1992, received Danjon ratings of L equals 0 from many observers. The moon was nearly invisible at mid-totality. Viewers scanning the sky with binoculars struggled to locate the lunar disk. The eruption of Krakatoa in 1883 produced similarly dark eclipses. The eclipse of October 4, 1884 was so dim that observers could barely make out the moon even though skies were clear. Sulfur dioxide particles in the stratosphere absorb red wavelengths, cutting off the refracted light that normally illuminates the eclipsed moon. Conversely, eclipses during periods of low volcanic activity, tend to rank L equals 3 or L equals 4. The moon glows bright orange or copper red with a vivid yellow or bluish rim around the umbral edge. The book of Joel, chapter 2, verse 31, states the sun will turn to darkness and the moon to blood before the great and dreadful day. Hagee and Biltz noted that the 2014 to 2015 tetrad coincided with Jewish holidays. The 4 eclipses occurred on April 15, 2014, October 8, 2014, April 4, 2015, and September 28, 2015. April eclipses fell near Passover. September and October eclipses fell near Sukkot. The timing is not supernatural. Jewish holidays follow a lunar calendar, so they always occur near full moon, which is the only time lunar eclipses can happen. Over the past 2,000 years, 8 tetrads have fallen on or near Jewish festivals simply because of calendar mechanics. No major apocalyptic events followed the 2014 to 2015 tetrad. Israel experienced ongoing regional conflicts, but nothing beyond the baseline level of tension in the Middle East. The term blood moon itself is not scientific. Astronomers call the phenomenon a total lunar eclipse. Blood moon is marketing language. Tetrads are not especially rare in the current era. Italian astronomer Giovanni Schiaparelli first noted that tetrad frequency varies over 600-year cycles. From 1582 to 1908, 0 tetrads occurred. From 1909 to 2156, 17 tetrads occur. The pattern ties to Earth's orbital eccentricity. As eccentricity slowly decreases over tens of thousands of years, tetrads will eventually become impossible. During the 21st century, 8 tetrads occur. The first ran from 2003 to 2004. The second from 2014 to 2015. The third will arrive from 2032 to 2033, with eclipses on April 25, October 18, April 14, and October 8. During the 300-year period from 1901 to 2200, the largest umbral magnitude of any tetrad eclipse is 1.4251 on April 13, 1949. For comparison, some non-tetrad total eclipses reach much deeper magnitudes. The eclipse of July 16, 2000, had an umbral magnitude of 1.7684. The eclipse of June 26, 2029, will reach 1.8436. Tetrad eclipses always have relatively shallow umbral magnitudes because the moon must pass close enough to the edge of the shadow to allow the 6-month spacing, but far enough into the umbra to achieve totality. During a lunar eclipse, the sun and moon sit 180 degrees apart in the sky. Perfect opposition. If one is above the horizon, the other should be below it, but Earth's atmosphere bends light through refraction. Atmospheric refraction lifts the apparent position of celestial objects near the horizon by roughly 34 arc-minutes. This is why the sun appears to rise several minutes before it geometrically crosses the horizon, and why it remains visible several minutes after it geometrically sets. During a total lunar eclipse, if the alignment occurs near sunrise or sunset, refraction can lift both the sun and the moon above opposite horizons for a brief window. On October 8, 2014, observers across eastern North America experienced a Selene lion. The moon set in the west during totality while the sun rose in the east. Atmospheric refraction kept both visible for 2 to 9 minutes depending on location and elevation. The phenomenon is more easily observed from high elevations. Mountain ridges, tall buildings, or aircraft extend the viewing window because the observer sees the horizon from a higher vantage point, gaining extra time before the moon geometrically sets. Observers near the Mississippi River had optimal conditions. Selenilions occur during every total lunar eclipse somewhere on Earth, but the combination of timing, geography, weather, and observer location determines whether anyone actually witnesses it. The term comes from French astronomer Antoine-François Payen, who published Selenelion ou apparition lunisolaire in 1666, after observing the June 16, 1666 eclipse from Paris. Ancient Greek astronomer Hipparchus reportedly observed a Selenid lion around February 7, 142 BCE from Rhodes. Pliny the Elder mentioned the phenomenon in his natural history, noting that Hipparchus recognized it 2 centuries before Pliny's time. Renaissance astronomer Tycho Brahe recorded a Selenid lion from his observatory in 1590. The phenomenon fascinated early astronomers because it challenged the simple geometric model of eclipses and required understanding atmospheric refraction and diurnal parallax to explain. A central lunar eclipse occurs when the moon passes through or very near the antisolar point, the exact center of Earth's umbral shadow. These eclipses tend to have longer totality durations and darker colors because the moon receives the least refracted sunlight. Roughly 59.6% of all total lunar eclipses are central. Non-central total eclipses pass through the outer regions of the umbra. resulting in brighter appearances and shorter totality. The difference is noticeable on the Danjon scale. Central eclipses often rate L equals 1 or L equals 2, appearing dark with gray or deep red coloration. Non-central eclipses frequently rate L equals 3 or L equals 4, glowing bright copper orange with vivid yellow rims. A micromoon eclipse occurs when a total lunar eclipse coincides with the moon at or near apogee. The moon appears roughly 12 to 14% smaller in the sky compared to a supermoon. Because the moon moves slower at apogee, totality lasts longer. In the 21st century, there are 87 total lunar eclipses. 28 are supermoons, 6 are micromoons. Almost all total lunar eclipses in Lunar Saros 129 are micromoon eclipses. The March 14, 2025, total lunar eclipse occurred 3.3 days before apogee, qualifying as a micromoon eclipse. The moon's apparent diameter was roughly 29.5 arc-minutes, compared to the average 31 arc-minutes. The reduced size is subtle to the naked eye, but measurable in photographs. Conversely, a supermoon eclipse occurs when totality coincides with perigee. The moon appears roughly 14% larger than at apogee. The most recent supermoon total lunar eclipse occurred on May 26, 2021. The next will happen on October 8, 2032. Supermoon eclipses have shorter totality durations because the moon races through the shadow faster at perigee. The combination of larger apparent size and deep red color makes supermoon eclipses especially dramatic visually. Eclipses repeat in families called Saros series. Each series contains roughly 70 to 80 eclipses spanning 12 to 15 centuries. Eclipses within a series share similar characteristics but shift gradually in geometry, latitude, and time of day. For example, Saros Series 113 began with a penumbral eclipse on April 29, 888 CE. It will end with a penumbral eclipse on June 10, 2150. The series contains 71 eclipses total, including 7 penumbral at the start, 23 partial, 13 total, 18 more partial, and 10 penumbral at the end. The March 25, 2024 deep penumbral eclipse was number 64 in this series. Each eclipse shifts roughly 1/3 of Earth's circumference westward because the 8-hour offset in the Saros period equals 1/3 of a day. After 3 Saros cycles, totaling 54 years and 34 days, the eclipse returns to roughly the same longitude. This is called the exeligmos cycle, meaning turn of the wheel in Greek. Ancient astronomers used Saros tables to predict eclipses centuries in advance without understanding the underlying orbital mechanics. Modern eclipse prediction uses precise numerical integration of lunar and solar ephemerides. NASA's Jet Propulsion Laboratory, DE-430 Ephemeris, provides positions accurate to within a few kilometers over millennia, enabling eclipse calculations with uncertainties under 1 second. At the moon's average distance of 384,400 kilometers, the umbra measures roughly 9,000 kilometers across. Earth's atmospheric refraction enlarges the effective diameter by roughly 2%. This enlargement varies slightly from eclipse to eclipse for reasons not fully understood. Observers timing when craters cross the umbral edge have measured enlargements ranging from 1.7% to 2.1%. The variation likely relates to atmospheric conditions, cloud cover along Earth's limb, and stratospheric aerosol content. During the July 1982 eclipse, 697 crater timings from sky and telescope readers yielded an enlargement of 2.1%, with a probable error under 0.1%. 6 months later, during the January 1983 eclipse, 298 timings gave 1.7% enlargement with similar precision. Temperature inversions, jet streams, and volcanic plumes all influence how much sunlight refracts into the umbra, altering both the shadow size and the brightness of the eclipsed moon. On November 1967, Surveyor 3 photographed Earth during a total lunar eclipse. Earth appeared as a black disk with a brilliant red-orange ring around the edge, every sunrise and sunset on the planet visible simultaneously. On February 2025, the Blue Ghost Mission 1 captured the first color photograph of Earth during a lunar eclipse from the lunar surface. The image showed the same red ring phenomenon in vivid detail. From the moon's perspective, a lunar eclipse is a solar eclipse. Earth blocks the sun. But unlike solar eclipses on Earth, where the moon is too small to block the solar corona, Earth is large enough from the moon's perspective to completely occlude the sun. The red ring is Earth's atmospheric edge, scattering and refracting sunlight. The dark side of Earth is still faintly illuminated by moonlight reflecting back from the lunar surface, creating a ghostly glow visible in long exposure photographs. Astronauts on the lunar surface during totality would experience eerie lighting. The sky would not go completely black because of the diffused light from Earth's glowing atmospheric ring. Shadows would appear soft and rust-colored. Stars would blaze brightly in the sky without atmospheric interference. The sun would remain hidden behind Earth's disk for over an hour during longer eclipses. A penumbral magnitude of 1.0 means the entire moon sits within the penumbra. An umbral magnitude of 1.0 means the moon just barely achieves totality with its edge touching the umbral boundary. Magnitudes greater than 1.0 indicate the moon passes deeper into the shadow. The deepest eclipses have magnitudes above 1.8. Umbral magnitude depends on the moon's path through the shadow and the distance from the umbral center. Shallow eclipses with magnitudes near 1.0 have short totality durations and bright appearances because the moon stays near the umbral edge where more refracted sunlight penetrates. Deep eclipses with magnitudes above 1.5 have long totality durations and darker appearances because the moon plunges into the shadow's center where less light reaches. The term magnitude in eclipse contexts differs from stellar magnitude. Eclipse magnitude is a geometric ratio, not a brightness measurement, though it correlates with brightness through the Danjon scale. The moon's orbital inclination of 5.14 degrees relative to Earth's orbital plane around the sun is why eclipses do not happen every month. The moon crosses the ecliptic plane at 2 points, called nodes. The ascending node is where the moon moves northward through the plane. The descending node is where it moves southward. Eclipses can only occur when the sun is near one of the nodes during a new moon or full moon. This happens twice a year during eclipse seasons. Each eclipse season lasts roughly 35 days because the sun's apparent diameter is roughly half a degree, and the node crossing window extends roughly 15 degrees on either side. If a full moon occurs within this window, a lunar eclipse happens. If a new moon occurs within this window, a solar eclipse happens. The nodes are not fixed. They precess slowly due to gravitational perturbations from the sun, completing a full rotation every 18.6 years. This is called the Draconic period. The Draconic month, the time for the moon to return to the same node, is 27.21222 days, shorter than the Synodic month of 29.5306 days. The interplay between these periods generates the Saros cycle and determines eclipse frequency. Sunsets worldwide glowed abnormally red. Lunar eclipses from 1884 through 1887 appeared exceptionally dark, rating L equals 0 or L equals 1. The moon turned dark brown or gray instead of copper red. Similar effects followed Mount Agung in 1963, El Chichon in 1982, and Pinatubo in 1991. The correlation between volcanic activity and eclipse darkness is strong enough that astronomers proposed using Danjon ratings as an indirect measure of stratospheric aerosol content. Observers worldwide, reporting consistent L equals 0 or L equals 1 ratings, indicate significant volcanic ash in the upper atmosphere. Ratings of L equals 3 or L equals 4 indicate clear stratospheric conditions. This method provides a crude but historically useful proxy for atmospheric transparency before satellite measurements became available. Recent studies have used digital photography to quantify eclipse colors through RGB color space analysis, defining a modified Danjon scale based on the normalized color vector magnitude. This FD number, or Danjon factor, provides an objective measurement that correlates with visual L ratings but eliminates observer subjectivity. Photographs of eclipses from 2000 through 2022 show clear separations in RGB space corresponding to volcanic activity. Eclipses following major eruptions cluster in the low red, low green region. Eclipses during volcanically quiet periods cluster in the high red, high green region. The moon's orbital eccentricity is 0.0549. Perigee distance ranges from 356,400 to 370,000 kilometers, depending on perturbations from the sun and planets. Apogee distance ranges from 404,000 to 406,600 kilometers. This 14% variation in distance translates to a 14% variation in apparent size. During supermoons, the full moon at perigee subtends roughly 33.5 arc minutes. During micromoons, the full moon at apogee subtends roughly 29.4 arc minutes. The average is 31 arc minutes, or roughly half a degree. Supermoons recur in cycles of roughly 14 lunar months, or 413.4 days. This is because 14 lunar months approximately equal 15 anomalistic months. The time from perigee to perigee, 14 times 29.5, 306 equals 413.428 days. 15 times 27.5, 545, 5 equals 413.318 days. The close match means supermoons repeat annually with an additional drift of about 1 month and 18 days each year. The closest supermoon of 2025 occurred on November 5 at 0545 UTC with a perigee distance of 356,833 kilometers. The next closest supermoon arrives on December 24, 2026, shifted by 14 months. Micromoons follow a similar pattern. The most distant full moon of 2025 occurred on April 13 at 406,006 kilometers. The most distant new moon occurred on November 20 at 406,680 kilometers. Red light has a wavelength around 650 nanometers. Atmospheric scattering is inversely proportional to wavelength to the fourth power, a relationship called Rayleigh scattering. Blue light scatters roughly 16 times more than red light because 450 to the fourth power divided by 650 to the fourth power equals 0.0625 or 1/16. When sunlight grazes Earth's atmosphere during a lunar eclipse, blue and violet wavelengths scatter away into space. Red and orange wavelengths penetrate the atmosphere and refract toward the moon. The amount of refraction depends on atmospheric density, which drops exponentially with altitude. Most refraction occurs in the lower troposphere within the first 10 kilometers. Ozone in the stratosphere absorbs some ultraviolet and blue light. Water vapor absorbs some infrared. Aerosols and dust scatter and absorb across all wavelengths depending on particle size. Larger particles from volcanic ash scatter red light more efficiently than small molecules, darkening the eclipse. Clear, dry air with minimal aerosols produces bright copper-red eclipses. Humid, hazy air or volcanic contamination produces dark rust-brown eclipses. The brightness and color also depend on which part of Earth's atmosphere the light traverses. Observers on the moon would see brighter light refracting through clear tropical air near the equator, and dimmer light through storm systems or polar regions, with more cloud cover. The integrated effect of Earth's entire atmospheric limb determines the eclipse appearance. If a major hurricane system or extensive cloud cover sits along the day-night terminator, the eclipse darkens. If clear high-pressure systems dominate the terminator, the eclipse brightens. The cooling rate depends on the thermal properties of lunar regolith. NASA's Diviner lunar radiometer aboard the Lunar Reconnaissance Orbiter has mapped lunar surface temperatures since June 2009. During eclipses, mission controllers shut down most instruments to conserve battery power, but leave Diviner active. The instrument measures how different rock sizes and compositions cool at different rates. Boulders cool slower than fine dust. Impact ejectablankets cool faster than compact bedrock. Crater floors cool differently than crater rims. These cooling patterns reveal the subsurface structure and particle size distribution. Scientists use Diviner data to create thermal inertia maps showing the physical properties of the lunar surface at scales down to meters. Eclipses provide a natural experiment for studying heat transfer without the sun's input. The rapid cooling also stresses rocks through thermal shock, potentially contributing to space weathering and regolith generation over geological time. Repeated heating and cooling cycles can crack rocks and pulverize them into finer particles. Ancient astronomers recorded eclipses with dates and descriptions. Modern eclipse calculations can pinpoint when and where historical eclipses occurred. By matching historical accounts to calculated eclipses, scholars can confirm dates and test calendar systems. For example, Babylonian cuneiform tablets describe lunar eclipses during specific kings' reigns. Calculating which eclipses were visible from Babylon during those time periods helps establish absolute chronology. Chinese dynastic records include detailed eclipse observations. Matching these to computed eclipses verifies dates and improves understanding of ancient Chinese astronomy. Ptolemy's Almagest describes 3 lunar eclipses observed by Hipparchus on March 23, 146 BCE, August 21, 145 BCE, and February 2, 144 BCE. Modern calculations confirm these dates with precision. Hipparchus used these observations to refine lunar orbit parameters, measuring the moon's distance and the length of the synodic and anomalistic months with remarkable accuracy for his time. Medieval European chronicles mention eclipses during battles, plagues, and political events. Cross-referencing these accounts with computed eclipses helps date otherwise ambiguous historical events. The reliability of eclipse calculations over millennia provides an independent check on historical chronology. Earth must be at maximum distance from the Sun, casting the largest possible umbra. The moon's path must cross the exact center of the shadow. This configuration is rare but not impossible. The July 27, 2018. Eclipse approached the maximum with a totality duration of 103 minutes. The eclipse of July 16, 2000 lasted 107 minutes according to some calculations, though official NASA figures list 106 minutes. Discrepancies arise from how one defines the start and end of totality given the diffuse edge of the umbra. Crater timing observations show the umbral boundary is not sharp but gradual, making the exact moment of second and third contact ambiguous. The shortest possible total lunar eclipse lasts only a few minutes when the moon skims the umbral edge at perigee near Earth's perihelion. The April 4th, 2015 eclipse lasted 4 minutes, 43 seconds. Observers reported the moon glowing brightly even during totality because it remained near the umbral edge where significant refracted sunlight penetrated. A supertetrad is an extremely rare sequence of 4 consecutive eclipse seasons, each containing both a total lunar eclipse and a total or annular solar eclipse, creating 8 full eclipses in a row over 18 months with no partial or penumbral eclipses. Only 2 supertetrads have been identified in the 6 millennium catalog from 2000 BCE to 4000 CE. The first occurs from 2043 to 2044. The second occurs from 3707 to 3708. The 2043 to 2044 supertetrad includes total lunar eclipses on March 22, 2043, September 14, 2043, March 11, 2044, and September 7, 2044. The intervening solar eclipses are April 7, 2043, September 29, 2043, March 26, 2044, and September 21, 2044. The first 3 solar eclipses are marginal, with the moon's umbral or antumbral shadow barely grazing Earth's surface. The rarity arises from the strict requirement that every eclipse season in the sequence must produce a total lunar eclipse and a full solar eclipse, with no weaker eclipses breaking the pattern. Over 6,000 years, only 2 sequences meet the criteria. Because a lunar eclipse lasts several hours, observers near the day-night terminator can see part of the eclipse as the moon rises or sets. Observers near the anti-sun point, the location where the sun is directly below the horizon at local midnight, see the entire eclipse from start to finish at high elevation. Visibility maps show which regions see the eclipse and at what phase. Penumbral eclipses that occur while the moon is near the horizon are difficult to observe because the sky is bright during twilight. Total eclipses with the moon near the horizon produce stunning photographic opportunities, as the red moon appears near landmarks or within atmospheric layers, creating optical distortions. Refraction near the horizon makes the moon appear vertically compressed. Temperature inversions can create superior mirages, raising the moon's image above its true position. Haze and pollution near the horizon can dim the eclipsed moon further or add color shifts. Observers at high altitude see deeper colors and darker skies, enhancing the contrast during totality. Aircraft flying at cruise altitude experience even better conditions with less atmospheric thickness between the observer and the moon. Observers on mountains above cloud layers see the eclipsed moon with the most saturated colors. Professional astronomers sometimes conduct eclipse observations from aircraft to ensure clear skies and extend the duration of selene-lion viewing windows. Polar regions see fewer eclipses because the moon stays low on the horizon or below it during winter months. On average, a total lunar eclipse is visible from any given location roughly once every 2.5 years. This is much more frequent than total solar eclipses, which appear at a given location roughly once every 375 years. Lunar eclipses are easier to observe because they are visible from entire hemispheres and last hours. Solar eclipses are visible from narrow paths and last minutes. Despite the rarity of solar eclipses, they generate far more public excitement because of the dramatic daytime darkness and the visible solar corona. Lunar eclipses are often taken for granted because they happen at night when many people are asleep and the visual effect is subtler. Nevertheless, lunar eclipses offer unique scientific and aesthetic value. They demonstrate atmospheric optics, celestial mechanics, and Earth's place in the solar system. Observing the moon dim and turn red over the course of an hour provides a tangible connection to the geometry of space. 57 are partial, 84 are penumbral. The distribution is not uniform. Some years have 4 eclipses, some have 2. The pattern depends on the alignment of the Saros cycles and the node positions. The year with the most eclipses in the 21st century is 2030, which has 4 lunar eclipses and 2 solar eclipses for a total of 6 eclipses. The longest gap between total lunar eclipses in the 21st century is 3 years, occurring from December 21, 2010 to December 10, 2011. The next 3-year gap occurs from September 8, 2025 to March 3, 2026. Wait, that is only 18 months? Recalculating? The longest gap is from September 28, 2015 to January 31, 2018, 2 years and 4 months. Between January 31, 2018 and July 27, 2018, only 6 months passed. The irregular spacing results from the complex interplay of orbital periods and eclipse seasons. Distance peaked at 406,680 kilometers, the greatest lunar apogee from Earth since January 22, 2007. At that distance, the moon subtended only 29.2 arc minutes, the smallest angular diameter for a new moon during this era. If a total lunar eclipse had occurred at that moment, it would have been the smallest apparent blood moon in nearly 2 decades, a micromoon eclipse at extreme apogee. None did, but the geometry was measured. The data sits in the ephemeris tables alongside every other configuration: numbers, distances, angles, light bending through atmosphere, shadows projected across space, no mysticism required. Color shifts. The mechanism is physics: Rayleigh scattering, atmospheric refraction, orbital geometry. The ancients saw omens. We see wavelengths and crater timings. Both groups watched the same sky. One built mythologies. The other built Saros tables and digital color vectors. On February 7th, 142 BCE, Hipparchus looked up from Rhodes and saw both the sun and the eclipsed moon in the sky at once. Selenilian. Impossible geometry made visible by atmosphere. He did not know the word refraction. He knew the observation contradicted the simple model, so he measured angles and built corrections. His numbers predicted eclipses for centuries. On December 9th, 1992, observers scanning the dark sky during totality could barely find the moon. Pinatubo ash. L equals 0, near invisibility. The numbers from Danjon's scale matched the sulfur dioxide concentration measurements from satellites. Atmospheric transparency quantified through lunar dimness. Volcanic forecasting through eclipse photometry. Every eclipse records atmospheric state. Red means clear stratosphere. Black means ash. You do not need prophecies. You need spectrometers and crater timings. And if you stand outside during totality, you see what every human who looked up has seen since the first eclipse. Earth's shadow, the moon glowing rust, every sunrise and sunset on the planet shining at once through the atmosphere onto that distant rock. Geometry, light, time.